All right, so let's get going. Now, does everybody remember a little bit about Vesper and Lewis structures that we had started? Okay. Okay. So the first thing you need to do with Vesper is you need to go ahead and draw out the Lewis structure, right? Did everybody see that I had uploaded some extra videos on drawing Lewis structures? If you haven't, if you go on YouTube, there are extra videos if you want some more demonstration of it, okay? Now, these right here are the Lewis structures for these formulas right there. Notice that we just do the same thing each time. We count up the number of electrons and valence electrons, and then we put the thing that needs the most bonds in the middle. That's the thing that's furthest away from the noble gas. We attach the stuff that needs less bonds with single bonds. Never start with double and triple because it'll cause you problems. Then we fill the stuff in on the outside first. Any extra electrons go in the center, right? Okay. And then, if we need to, we move lone pairs of electrons that aren't in bonds, into bonds if we need to fill up the octets. Okay? Okay, so right here we have these three different Lewis structures. What sort of shapes would those take on? Okay, so we look at the electron groups, or the electron domains, as I would say, around the phosphorus here, right? Which is the central point. Excuse me. And this is going to be, well, that's 1, 2, 3, 4. Weird. Is that showing up and then popping away on your end too? Isn't that weird? Okay. Anyways, 4 groups around there, right? 4 domains. Okay. Now, those are the electron geometry. So the electron geometry is 4 domains trying to get as far apart as possible, which is tetrahedral, right? Yeah. And it looks a bit like a camera tripod. Okay. All right. So what would be the molecular geometry then? What's the difference there? So do you normally call a molecule the electrons? Is that what you normally refer to the molecule as? No. You usually refer to the molecule as the atoms, right? So the molecular geometry is just the atoms. Okay? So the molecular geometry is going to be the geometry that remains, and that would look like a pyramid. Can everybody kind of see that? Okay. All right, so this one right here, can anybody tell me what that geometry would be? Bent. Yeah, that'd be bent, right? I have to do that. It's in my contract. All right, this one over here, what geometry would that be? Tetrahedral again. You got it. Okay, fantastic. All right. So let's go ahead and talk a bit about polarity of molecules and the intermolecular forces. Now, covalent bonds in the molecules, these can be nonpolar, where they share the electrons exactly equally, or they can be polar. Polar means that they have a positive and negative end for that bond, right? And so in this case right here, we actually have 4 polar covalent bonds. Can everybody see it okay? See the arrows pointing out towards the chlorines for each one? Okay. And so each of those chlorines is negative. That carbon in the middle is positive. Okay? Okay, so what does this mean? Well, if we look at these, they're like magnets, right? What would happen if we equally pulled something in every single direction? Is it going to move anywhere? Yeah, it's just going to stay in the middle, right? And that's what's going to happen here. This is going to end up having all of these different forces cancel out, isn't it? And that's going to end up having no overall, what we would call a dipole, meaning no overall poles for the molecule. Okay? Can everybody get that concept? Okay? Fantastic. This is why, for example, most compounds and most substances that you deal with don't really have any charge to them. They don't really have any poles on them. They don't act as magnets, right? Okay. Okay, so this right here is what is referred to as a nonpolar molecule. It's one that doesn't have any overall dipole. Now keep the separation in your mind. I have bond poles, right? I have molecular poles. Okay? I can have bond poles and not have a molecular dipole. Okay? So I can have polar bonds, no molecular dipole. I do have to have polar bonds to have the possibility of having a dipole for the molecule, though. Okay? But if they all cancel out, I'm not going to get an overall dipole, right? This is another case right here. This is actually CO2, carbon dioxide. Interestingly enough, this right here is actually hinting at the entire concept of global warming. This little diagram here. That's actually why CO2 absorbs in the infrared and can act as a greenhouse gas. Anyways, and this right here is tetrachloride. Again, no overall pole. So these are considered nonpolar molecules. This right here is a polar molecule. See how the bond dipole doesn't have anything to cancel it out? So the molecule ends up with an overall pole, doesn't it? Right. And again, that's because one end is positive, one end is negative, right? Fantastic.
You said the one with the more valence electrons would be the one that pulls the other one?
The one with greater electronegativity. Now, the trend for electronegativity is going up and to the right. So that's probably where you were thinking of the valence electrons?
Yeah.
Yeah.
Okay.
Because, like, fluorine has a higher electronegativity and will pull electrons from oxygen, for example. And oxygen pulls electrons from most of the other stuff. Yeah.
Okay.
And so chlorine, fluorine, and oxygen are actually a lot of the poles that you see in molecules. Nitrogen being the one that's a bit of a flip. Okay, this is another polar molecule right here. Anybody recognize that molecule?
Water.
It's water. Yeah. So why does water have the properties it does? Because it has polarity. Actually, it's very strong polarity. Okay. And so water has an overall dipole. Notice when we look at this dipole, the bond's polarity actually negates each other a little bit, don't they? Can everybody see that? The side-to-side horizontal actually gets canceled, doesn't it? Yeah, it's only the vertical that you end up having an overall dipole. Okay? Okay, everybody comfortable with these so far? I'm losing anybody? Okay, think of them as little magnets. Okay? If I have two little magnets and I'm pointing them this way, I'm not going to have any overall magnet properties to do stuff with, right? Yeah. If I point them in the same direction, I'm going to get overall magnetization to work with, right? I can do things like attach it to a fridge. Or attach it to another magnet, right? Yeah. And that's what I want you to have in your head. These are little magnets, okay? If it helps, you can actually think of them as, you know how everybody played with Legos when they were a kid, right? And had your little box of Legos? Sometimes a big box of Legos. Yeah?
They hurt to step on.
Yes, they do. There's the ones with the magnets in them, right? There's the ones without the magnets, right?
You have Legos with magnets?
Really?
Yeah. You don't have Legos with magnets?
What?
Never.
Wow. That is so sad.
They do. It's like a mix like each other.
I'm almost 30 and I've never had
You
Legos.
can, yeah, there are Legos with magnets.
I feel like you're
That's not
lying.
like Lincoln
No, no.
Logs or something?
Oh yeah, look it up.
Lincoln Logs definitely don't have magnets.
No?
No.
No, definitely not.
No, you do snap together the Legos, but some sets of Legos have magnets, so you can do things like close the cockpit and it'll stay closed. Yeah.
Really?
Yeah. Oh yeah.
I think you.
No.
That's what I'm saying.
Or maybe the magnetic tiles have magnets. Like the.
That's true.
Oh, those?
Like those?
No. I'm saying there's actual Legos. The company that makes Legos makes a series of ones that has magnets in them.
Holy shit, he's not lying.
There is.
Oh my god.
They actually have ones that have little.
And apparently,
That
this
was
is a
our
thing that has
generation.
aged out.
I mean, I'm almost 30. I've never heard of this.
Yeah.
That's
I was about to say that.
okay. That's just sad. Okay. Has anybody had toys with magnets in them though?
Yeah.
Yeah, of course.
Okay, and you throw them in your little baggie with the other toys.
Those two magnets that stuck together. So.
Yeah. Okay. Okay. So we can relate to the idea, but apparently not with Legos because everybody got shitty kits for Legos.
Yeah.
I'm definitely gonna buy magnetic Legos tonight, just for the fun of it.
Oh yeah, you can do some cool stuff.
I'm gonna do that.
Yeah, like a big one was. Have you guys ever seen that one where the Lego character is like climbing up the wall?
Yeah.
Yeah.
That one's a magnet Lego set.
Oh, that makes sense.
That's how you attach the damn character climbing on the wall.
Well, I mean, Legos are blocks. You just push them in the hole anyway.
Yeah.
No, the one where he's climbing a flat wall.
I vaguely know what
Anyways.
you're talking about.
Yeah, anyways, it's okay. Your guys' sad excuse of Legos. Okay. So, again, here's another one. Ammonia has an overall dipole. Everybody's good with that, right? Has anybody noticed something?
The arrows being balanced.
The arrows be balanced, but another thing is, like, a lot of the stuff I've been describing without an overall dipole is not soluble with the stuff I was describing with an overall dipole, right? And so these are referred to as nonpolar and polar compounds, okay? Or nonpolar and polar molecules. Okay, if you are not already attached to this slide, go ahead and get attached because I will ask a question in just a bit. Okay. Okay, and the question I'm going to ask in a bit is determine whether a molecule, OF2, is polar or nonpolar. So I want you to start thinking that through. Is it polar or nonpolar? And then what I'm going to do is I'm going to go on to this next slide, which you can still register on. And this is the get ready. Does anybody need more time to think? OF2. Is that going to be polar or nonpolar? Okay. Okay. Try your best. Think through how you would figure that out. Okay? There's two parts to figuring it out. Hey, okay. And so, everybody ready? Set. Go. Dun, dun, dun. I know. Nerve-wracking, right? I'm continuously challenging you. Making you think. Wicked. Really. Just wicked. Okay. And so, it is polar. That is correct. And why is it polar? Well, there's two parts to this. First off, you have to figure out, is it going to have a polar covalent bond? And so oxygen and fluorine, they have a significant electronegativity difference. And so they will have a polar bond, one thing. And then the second part we have to figure out is this going to add up to an overall molecular dipole? Okay? And so we would have to write this out in a three-dimensional-ish way so we could figure out, are they going to cancel out? Okay. Now, in this case, you could actually go, hey, this looks a lot like H2O, doesn't it?
Yeah.
You have something that normally wants one bond. There's two of them. They're bonded to oxygen, aren't they? I know H2O is bent, isn't it? So I'm going to have an overall bond dipole. Okay? That's one way you could think of this. You could just take molecules you're used to and you already know, and you can do like that. Okay? And so again, in this case, we're actually going to have a positive side up at the oxygen and a negative side down at the fluorines. It's like reverse H2O. Okay?
How do you do the first step? Like, how are you supposed to find if it's polar?
So you don't actually need to find the number when you're doing this. You just need to see, is there a fairly significant difference between the electronegativities? In the case of oxygen and fluorine, which are up there at the top right, there's a significant difference.
Wait, how?
That's because as you get further up and to the right, that's where you get the large differences
Oh, okay.
in electronegativities.
Okay.
Yeah. As you go left, you actually get smaller and smaller differences as you get over left.
So that would be polar up there?
Yeah, if you're basically if you have things like oxygen bonding stuff and fluorine bonding stuff, they're always going to end up being polar
Okay.
because they're just very strong. And at that point, you're getting very strong stuff pulling electrons from things.
Okay.
Okay?
Same with calcium. Oh, I'm sorry. Never mind.
Calcium?
I was thinking chlorine. Never mind.
Oh, chlorine would be number 3.
That's what
And then nitrogen after that. And then after those, they all become a lot weaker.
yeah, because like boron is close to this.
Yeah, and carbon's pretty weak compared to those. And so after you get past fluorine, oxygen, and chlorine, your likelihood of getting significantly polar covalent bonds is pretty low. Yeah. Yeah, there's a movie or something being played. I can close the deal if you need. No, it's not just you. Don't worry. Yeah, the chemistry hasn't cracked you yet. Okay. So the next part is once you figure out if there's going to be a bond dipole, you need to figure out if there's going to be a molecular dipole, right? And that's where you need to get into the three-dimensional VSEPR. Okay? And so in this case, we're bent. That means they can't cancel out. There has to be an overall dipole, doesn't there? Okay. Okay, let's try the next one. Identify each of the following molecules as polar or nonpolar. Okay. So is there going to be a reasonably significant difference between those polarities? One of the hints here is halogens in general are something that typically gives you polar stuff, unless it's bound with the same thing. Okay. So PBr, the bonds are going to be polar, aren't they?
Yeah.
Yeah. Okay. So here's the next question. Is this going to have an equal pulling in every direction, or is this going to have an asymmetry? I.e., yeah, asymmetry meaning it's not equally pulling in every direction.
I think
Yeah. Asymmetry? Okay. You are correct.
Okay, it's like, isn't the P in the middle and the BR?
Yes, but it's not flat. It is a trigonal pyramid.
Yeah, that's what I was
Yeah.
trying to do.
Okay.
Yeah, that.
Yeah, and that's because it has the lone pairs up here.
Okay.
Yeah, I couldn't tell the difference because there was also trigonal planar, which a bit of had it cancel out, right? Okay. Now, how about HBr? Non?
I would also
This
say
is the bond polar first.
it is.
It is.
Non-polar?
No, it is polar.
It
Because
isn't.
beryllium
No,
is
it's
a
polar.
halogen, and hydrogen is one of the first.
Yeah. Bromine is a halogen. Hydrogen
So
is one of the weaker
has
ones.
to be up there for it to be polar.
So, again, that's why I keep going through that first off, you need it to see if is it going to be a polar bond. Okay? It's going to be a polar bond if there's a significant difference on the periodic table, or if one of them is something like a halogen, oxygen. Those are typically going to be polar. Okay? And one of the things you need to do is look again at that electronegativity table and extract that pattern from it, okay? Okay. The next part you always have to do is it going to cancel out overall? Okay? And that's why I keep asking you those two questions. I'm trying to get you to connect with that process, to deductively reason through it. Okay?
So how would we know if it's canceling out? Like if it's flat, like 1, 2, 3, 4, like a cross kind of?
Yeah, if you have a cross or if you have a triangle shape and they're all going to be in a plane or canceling.
Isn't that one triangle, the P?
No, it isn't.
That looks,
It's a pyramid. Like this.
Okay. Okay, yeah, yeah. Oh, okay.
It's got phosphorus on the top.
Can you show me like a triangle example of kind of like
That'll be like
H2O?
H2O is in triangle. That's bent. I was actually referring to like a BH3. That would be what's called trigonal planar. Okay? And so that would have a B in the middle, and they would have H's all around it in a triangle configuration. That's that trigonal planar that we talked about before.
Okay, so why is it like that, but the P and then BR?
It has no lone pair. That's why I referred to that has a lone pair. That's why that is trigonal pyramidal.
What?
And when he does beryllium, and when he does boron and the free hydrogen, all the valence electrons are 4. Whereas when he did the PBR, there's still, I think, 2 remaining valence electrons.
Okay, we're going to have to move on.
Okay.
Okay, so yes, this is polar. Again, that's because the bond is polar, and there's only one bond, so there's nothing else to cancel around. That's it.
Okay.
Okay, this one right here is CF4. This one, the CNF, is that bond going to be polar?
No.
Yes.
Is it not?
It is, because
No.
there's
No.
significance between carbon and
Okay, what's the most electronegative thing on the periodic table?
fluorine.
Fluorine. And carbon is not the most electronegative thing on the table, right?
Oh.
And so it will be polar, bond-wise. Bond-wise. Now, will those bonds cancel out? That's the second thing you always got to consider, right?
Yes.
Okay. And so 4 things around a central point, that's going to be tetrahedral. That will have 1 in every direction on it. And so that's non-polar, yes.
Okay.
Yeah. So overall, this is non-polar
Oh.
as a compound.
Okay.
Okay? Okay. All right. And there we go. By the way, this right here for the CF4, this would be very, very positively charged on that carbon. Okay? It would actually have a full charge, like an ionic compound. Yeah, it's pretty crazy. Now, ionic bonds, these are going to be some of the strongest attractive forces that can exist between compounds. This is actually what's referred to as intermolecular forces. Everybody's aware of the interstates, right? Or internet. Why are those things called inter? Anybody ever heard of a intranet?
Is it like strong? Like
So inter means that it's between states. An internet is between networks. Okay?
okay, yeah, that makes sense.
And so intermolecular means that they're between molecules, not within them. Within them would be intramolecular. Okay? And so these are the connections that form between molecules or between compounds. Ionic compounds are going to make the ionic bonds are going to make some of the strongest connections that can exist between compounds. Partially because you're actually kind of talking about like a bond, aren't you? So it takes a lot of time, energy to break that. Okay? And this is why salts, like sodium chloride salt, melts at 801 degrees Celsius. That's why you've never seen a salt melt, and it's why you've never smelled a salt, except for like something that actually reacts and makes a gas. Okay? Because salts just take so much energy to break them apart that it's not happening at room temperature. Okay? Or anything even close to room temperature. Now, the next strongest ones are going to be things that have dipoles. Dipoles are like little magnets. They're going to attach together, and so they'll form pretty strong connections. Now, the force that is referred to as is dipole-dipole attractions. This is the force that exists between compounds, called the intermolecular force, that's going to hold these molecules together. And this force is the force you have to overcome if you try to melt it or if you try to boil it. Okay? So when you try to boil something like HCl, or if you tried to melt it when it's frozen, what you're going to be doing is you actually have to break these intermolecular force connections, or these dipole-dipole attractions. Can everybody see these dipole-dipole attractions okay? Remember how we had the two dipoles? What happens when you take a bunch of magnets and throw them in a bag together? They snap together, right? Positive, negative over and over, don't they? Same thing's going to happen here. Just like you threw a bunch of like fridge magnets into a bag, and they all, snap together. Whenever you put these in a solution together, they're going to snap together. Okay. And positive and negative will align. Now, hydrogen bonds, you may have heard of hydrogen bonds before. They're what hold together things like water, okay? Also things like proteins, etc. Sugars, or why sugars dissolve. Hydrogen bonds are just very, very special classification of dipole-dipole interactions. Okay? They're just really strong dipole-dipole attractions. That's it. Hydrogen bonds are going to happen where we have a hydrogen attached to a fluorine, oxygen, or nitrogen. What do those all have in common, by the way? They all have pretty high electronegativities, don't they? And a lone pair. Yeah, so what's going to happen here is when you have a fluorine and hydrogen that are bonded together, when you have a oxygen, a hydrogen bonded together, when you have a nitrogen and hydrogen bonded together, what's going to happen is that you'll get a very, very positive end that's very concentrated, very small. And then you're going to get this very negative end that has this very negative concentrated spot on it, which is the lone pair. Okay? And the hydrogen is actually going to be attracted to the lone pair of the other molecule. Okay? And this is going to make a hydrogen bond. This is what keeps things like DNA together. This is what keeps sugars dissolved in your bloodstream. This is what keeps most proteins in the shape that they are. Okay? This is actually one of the most important forces in your life. That's why I know life can exist without water so far. Okay. These are the hydrogen bonds, by the way. They are not molecular bonds. They are, again, intermolecular bonds, okay? They're the things that hold molecules together between each other. Okay? Okay. So, in terms of strength, we have ionic bonding, strongest, right? We have hydrogen bonding. That's going to be your next strongest. And then we have dipole-dipole attractions, which will be your third strongest, okay? And just remember that hydrogen bonding really is just really strong dipole-dipole attractions, right? Very similar, but just really strong ones. Very concentrated ones. Okay, so the last force that I need to mention, these are going to keep, again, your molecules together when you try to boil them, is dispersion forces. Now, this last one exists all the time everywhere, okay? When I was talking about water being held together before, the water is also experiencing dispersion forces, okay? When I'm talking about the hydrochlorides being held together, we're also having dispersion forces. NaCl being held together, also having dispersion forces. Now, If I anchor you down with a chain or a rope, are you going to worry if somebody ties a string to you?
No,
No. You're not going to care if somebody ties a string to you. But has anybody ever seen, what is that, Oliver's Travels?
I think so, a long time.
With the Lilliputians, and they tie them up with the string?
Gulliver's Travels?
Gullivers, yes, thank you.
This,
I
okay.
remember that.
This
Yeah.
analogy you're using about chains, ropes, and strings makes me think of how they used to tame elephants for circuses. When they were babies, they would tie them up with chains to pegs, and the baby elephants would never be able to break the chain. But when they grew up, they would swap it out for a rope. But since a rope and a chain would pretty much look the same to an elephant, it would already know that it can't break the rope, despite the fact that a full-grown elephant would probably be capable of breaking even the chain. So it just never bothered to try.
So the importance of the analogy is that dispersion forces are like the twine. It's like the little tiny pieces connecting, okay? They're not very strong individually. When you normally just ignore them because you have a stronger force to deal with. But when they're the only force, they're the only ones that matter, right? And they can build up tremendously. These are actually the forces that hold together things like oil and engines and tar. Okay? Dispersion forces. And those are examples where they built up tremendously, right? But it's also the force that's holding together gasoline. Gasoline evaporates all the dang time, right? So, yeah. Individually, dispersion forces are weak. Together, when you add them up a bunch, they become quite strong, okay? Yeah. Okay, so these are going to be the weak attractions that's going to exist between nonpolar molecules. Specifically, it's usually stated that way in every textbook because in nonpolar molecules, they're the only attraction. So they're the only attraction that matters in that case. But they exist all the time everywhere. Okay? Okay. You just don't care usually. These are going to be caused by temporary dipoles that are going to develop when molecules are near each other. Okay? They're going to be weak, but they make it possible for nonmolar molecules to form things like liquids and solids. Again, you can build up to become something that's quite hard to actually melt due to these connections, these dispersion forces. Because they're everywhere, they're ubiquitous all the time. If you get really big structures, then you have a whole lot of dispersion forces. Okay? And that's why you get something like a C60, 60 carbon atoms on it. All of a sudden, it has 60 chances of dispersion forces happening. And so you get, 60 pieces of twine. That's like a pretty thick rope, isn't it? Yeah. Okay. And so this is actually how this occurs. Now, if you have a bunch of objects and you throw it up in the air, what pattern are you expecting it to take when it falls back down?
You're not.
It's going to mostly have like a scatter around the middle, right? Okay. But when it falls down, does it perfectly have a symmetry where every single, like you count 20 and 10 are on the left, 10 are on the right? It's perfect? No. Look at the classroom around you. This was a mostly random filling into the room, right? Are you guys even? No. Yeah, I have a way bigger concentration on the right, my right, and a significantly smaller concentration on my left, don't I? So you're not quite even, are you? Yeah, like noticeably different. Now, what if you were charged? You're all electrons. This side would be negative, right? And this side would be positive. And I would have created a dipole. Okay? And so that's happening around molecules and around atoms all the time. These electrons are shifting around, and the probability states that they have to take on symmetric states a pretty decent amount of time, right? Where one side's going to be positive, one side's going to be negative. Is that making sense?
We're even.
Are you actually totally even?
There's 17 on each side.
That is unusual.
I just
Really?
I guess they're just spaced out.
Oh, because it's the back. I can't see the back. Yeah, as well. That's why.
Sorry, didn't want to ruin
No,
your
no.
but I was like, oh.
No, that's actually unusual. Like, that being even is actually quite unusual, right?
Yeah.
Yeah. It's just like, how often does the average happen? People always think they're going to get an average. They go in a casino and think, I'm going to perform the average, right?
Definitely not.
No, the average actually doesn't happen that often. The majority of times are actually going to be either on the positive or negative end. Okay? And the tail ends, like one person in this world lost every single time they played roulette. And one person in this world won every single time they played roulette.
Sounds like you've been hanging with Dr. Mason.
Oh, is it?
She teaches statistics of behavioral, and we're like talking about the 99%, the 1% of the tails occurs.
Yep. They have to occur, right? Yeah. Now, interestingly enough, I'm a tail end, like big time. I have actually rolled a 1 out of 20 over 25 times in a row. And I have also rolled double ones on 2 6-sided dice, playing backgammon. The game ended at 16 because the person I was playing against actually rolled double sixes the entire time with not loaded dice, same dice as we'd always used. And so I just barely exited on one side and the other
So
person's already
You're
done.
really good at like that gambling stuff and all.
No, I'm actually terrible because I have no luck.
Oh, okay.
Yeah. All games
So
of
you
gambling
lost a
have
lot,
luck.
But you rolled good, but you lost a lot.
No, I roll terrible. Like, I'm somebody that...
That sounds pretty good. One goes every time.
You don't want ones.
No, that's really, really, really bad.
You
Oh, I
prefer
thought
the
ones
sixes.
were good.
No, it's
No,
really
this is
bad.
not golf.
Yeah.
I'm
Yeah.
thinking golf.
Like, backgammon, that's really, really bad. And in general, rolling double ones would be really bad. It's called snake eyes.
I did not know that. Okay.
And in general, I'm somebody that could walk in. I don't gamble. But I'm somebody that has walked into a casino, put $20 in, and in the slot machine, you're supposed to win every other one. Minor wins that won't really change anything. But it's to keep you hooked. Because people like the flashy lights. I have actually pulled 20 times and never experienced a win. Yeah.
Not even
Yeah.
like $5.
No, nothing.
Oh my gosh.
Yeah. Like if I go in a casino and put 20 bucks in, it's like 10 seconds. Ding, 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 ding,
Those
done.
are the most fun. I love those.
Oh, they are not fun
Do
for
you
me.
do penny slots?
I've done it, and that's exactly what I'm talking about, and I don't win.
Oh.
Shit. It's bad. I can win the strategy games, but I would have to count or something like that, and casinos don't like that. So, yeah. Anyways, so this is actually how this works. Dispersion forces are just statistical probability at work. Okay? The electrons are uneven, and so this is going to make a dipole around that atom, right? And if it's near another atom, then the electrons on the other atom are going to get pulled towards it, right? See that? Positive end on one pulls the electrons of the other. Now, because they're near each other and they're sort of drifting near each other, they're going to start lining up. Their electrons will get pulled over for one. It will match the positive charge of the other. Once that starts reversing, it's actually going to go ahead and reverse the other way. These electrons will repel each other. These electrons will repel each other, right? And so they'll move. And then they line up again, don't they? Yeah. And so temporarily, just for a few nanoseconds, you're going to have a matchup, and they're going to pull themselves together. Okay? Kind of cool, huh? Yeah. Okay. So your melting points of compounds. These are actually related to the strength of the attractive forces between molecules or compounds. The lower as a result of weaker forces that hold them together. For example, most compounds with dispersion forces are going to have very low melting points. Okay, this is why things like olive oil and gasoline melt very easily, is because they have dispersion forces only. They're not particularly large molecules, and so they melt fairly easily. They're going to be higher as a result of stronger attractive forces like hydrogen bonding. This is why water has a significantly higher boiling point and higher melting point than something like gasoline. Okay? You guys have probably never even seen gasoline freeze, have you? Yeah, it freezes at very low temperature. So, now, anybody ever noticed that alcohol freezes at a lower temperature than water?
Yeah.
Okay. That's because alcohol has hydrogen bonding, but it has less hydrogen bonding than water would. Okay? All right, so the highest ionic compounds are going to be a result of strong attractive forces between the ions in the compound. These ones are going to be very, very difficult to melt or boil because they have extremely strong forces. And you can predict the relative melting and boiling points between different things by what type of forces would hold them together. Okay, and these are some of the different forces right here. Here we have ionic bonds, here we have hydrogen bonds, and here we have dipole-dipole attractions and dispersion forces. Everybody okay with that? And see how it predicts the trend quite nicely, doesn't it? Yeah. All right. So let's compare the bonding and attractive forces. Again, we have the ionic bond here. And so those have very high attractive forces between the molecules. Here we have covalent bonds, and that's going to have a bit lower strength. Right over here we have the molecules, and they're going to have hydrogen bonding. That's going to be the strongest of those between the intramolecular forces. Here we have dipole-dipole attractions, next strongest. And then we have the temporary dipoles or dispersion forces. Okay? And those are going to be the weakest ones of those. Now keep in mind again, if you start stacking up strings, you can get very strong, right? What is a rope? It's a bunch of strings knotted together, right? Okay. Okay, so let's try this out. Identify the main type of attractive force that are present in liquids of the following compounds: ionic bonds, dipole-dipole, hydrogen bonds, or dispersion forces. Okay, now the big hint for ionic bonds right here is if you have ionic bonds, they have to be what? You have to have an ion, don't you? See, those are going to always be ionic compounds. The other ones are going to be covalent compounds. Okay?
So the covalents are like up there, right?
There's a selection of different ones. We have ionic and covalent compounds here. Ionic compounds are going to have ionic bonds. Covalent compounds can have the other ones. Okay? So the first one I'm going to ask you is hydrogen bonds. And that's going to be a quiz. Is everybody ready? Have it in their head? Have an idea? Hydrogen has to be with what to be hydrogen bonding? Think of that. Okay. Okay. So everybody get ready. Okay. Ready? Set. Go. Which of those have hydrogen bonds as their intermolecular attractive force? Okay. Now, that is correct. Yeah. We got water, and we have NH3. And the one you're looking for here is that hydrogen is bonded to fluorine, oxygen, or nitrogen, right? If hydrogen is bonded to those, they have the possibility of hydrogen bonding. Okay? Okay, so the next one's going to be the main attractive force as hydrogen bonds. Okay, so now we're going to go ahead and do the rest of them. So NCl3, this one right here is a dipole-dipole attraction. And that's because it has an overall molecular dipole, isn't it? Okay, so overall molecular dipole gives you a dipole-dipole attraction. The H2O and NH3, we discussed that already. Those are hydrogen bonding. And then Br and Br. What is that going to be? Is there anything else? No. Br with Br, there's neither one stronger. You don't have any hydrogen for hydrogen bonding. There's no ions. You can't do anything else. And so the only one we can say is dispersion, right? Yeah, so that's going to be dispersion forces, because that's the only force available. Okay? Now note that all of these had dispersion forces. It just wasn't the primary concern. It was so weak it didn't matter. Okay, this one right here, that's a metal and a nonmetal, and metals and nonmetals are going to give you what? An ionic compound. Ionic compounds will do ionic bonds. Yeah. Okay. And that is the chapter. Woo. That was a long one, wasn't it? Yeah. Okay. Let's go ahead and go on to the next chapter.